The next step in deriving the DFT is time limitation. We'll start again with the sample signal xs of k. To calculate the DFT, only a finite number of samples can be considered. For example, the n signals for k equals 0 till n minus 1. In order to mathematically describe this extraction of n samples from an infinite amount of samples, we'll introduce this shifted rectangular signal of height 1 and width n ts. Since ts is the time between the samples, exactly n samples can fit into this rectangle. So the time-limited signal can be understood as a multiplication of the sample signal with infinite range and the rectangle. This rectangular function is often referred to as a window and denoted by w of t. This particular window is the boxcar or rectangular window. The time-limited or windowed signal is hence often referred to as xsw of k. And the process of time limitation is also often called windowing. To understand the effects of windowing, we'll go back to the frequency domain, where the spectrum of the boxcar or rectangular window w of t is the sinc function denoted w of omega, so that xsw of omega, the spectrum of the sampled and time-limited or windowed signal, is the convolution of xs of omega and the spectrum of the window. There also exist other windows, for example the Bartlett or triangular window, which, instead of just taking the samples and multiplying them by 1, as in the boxcar or rectangular window, or discarding them, the sampling values are multiplied with the height of a triangle at the particular sampling instance. The spectrum of the triangular window is a sinc squared. Its main peak has twice the width compared to the sinc resulting from the boxcar window, but the ripples decay much faster. As a result, when using a triangular or Bartlett window, the spectrum xsw of omega will have wider peaks but less ripples. Another option is the Hamming window, which is one full period of a cosine scaled and slightly shifted upwards. The peak of its spectrum has the same width as the Fourier transform of the triangular window, but its ripples are extremely small. Hence, when using a Hamming window, that is, multiplying the samples in the window with the height of the window at this particular sampling instance, the spectrum of the sampled and windowed signal, namely xsw of omega, will also have almost no ripples.